Okay, so in this screencast, we're going to be talking about more complex ions, or I'm sorry, ionic compounds. And if you recall, the last time we talked about how ionic compounds are simply a combination of ions. So if we took a +1 sodium and combine it with a -1 chloride, they'd combine and balance out so there'd be no charge and form sodium chloride. And remember how we name these things. You name it by the name of the metal, followed by the name of the non-metal with IDE as a suffix for it, so sodium chloride. And then I also did things like magnesium, and then the sulfur, all right, ion is 2 minus, and so this would be magnesium sulfide. Now, it's super easy when the charges match, right? Just like that, because then you combine them and you don't have to worry about it. They just combine beautifully in the same way that we see sodium chloride has combined with magnesium sulfide here. But what if things get a little bit more complex? For example, what if we decide we're going to go ahead and take magnesium, which we know is a +2 charge, and instead of combining it with the sulfur ion, sulfide, we're going to combine it with the chloride anion. Now, let's step back here for a moment and see and understand what's going to happen here. Ultimately, whatever we create, the ionic compound we create, it must not be charged. It has to be balanced. And so, let me just take a little bit of a metaphor here. Imagine that you're playing on the playground and you have a huge kid, right, on one side of the seesaw, and then you have a really tiny kid on this side of the seesaw. That's not going to work very well because obviously the seesaw is going to tip down in this direction, and that doesn't make any sense. It's going to be impossible for you guys to have a good time. So what you do here is you might need to, in order to balance this out, you might need to add 3 little kids so that this thing would balance out and 1 big kid would be equivalent to 3 little kids. And it would balance because neither side would touch the ground. Well, in a sense, that's exactly what you're going to do when it comes to combining an anion and a cation that have different charges. You need to make sure that their charges balance out so that you level out the seesaw. And in this case, instead of imagining that we have little kids here on a seesaw, imagine that the weight that we have here is the charge associated with something. And so on this side, with magnesium, you have 2 positive charges. All right, so that's a single magnesium cation over on that side. And on the other side, you have a single chloride ion. That's not going to be too helpful because the magnesium charge is going to outweigh the chloride charge, and it's going to cause the chloride to go up, the magnesium to go down, which we can't have. We need to make sure it balances. So what do you need to do? Well, it's just like adding 2 little kids on one side and for the 1 big kid on the other side. So I put another chloride over here with its negative charge. Now the charge is balanced. I have, as you can see here, I have 2 positive charges here to balance out with my 2 negative charges. But of course, if that's the case, I have to make sure that I represent having 2 chloride ions in this interaction. So I take my magnesium, I only have 1 of those, and I take my chloride anions, but the chloride then has to be balanced. And I have to show that there are 2 of them by putting a subscript here of 2 to indicate that I need 2 chlorides for every 1 magnesium. All right? So that seems like a pretty easy thing. You could imagine it would be in the opposite direction. Let's take, for example, geez, I don't know what happened there. It totally just froze. I hope this is going to work. Let's go back in here. So imagine I have, instead of magnesium, I take sodium, which is a +1 charge, and I want to combine it with, I don't know, let me pick something more interesting. All right, let's say I want to balance this, or I want to combine it with germanium, Ge. And germanium has, oh wait, I can't do, what am I smoking? Jeez, Chang, you can't do germanium. It's a cation. So instead, let me choose selenide, selenium's anion. So selenide looks like that. And of course, in order to balance this, I'm going to need to have 2 sodiums for every one of my selenide anions. Right? So how do I do that? Very simple. Take the Na. Oh, boo! Erase that. Take my sodium, and since I need 2 of those, have a subscript of 2 with my selenide ion, like that. Now, a lot of textbooks and teachers like to explain that you do what's called a crisscross method. But you simply take the absolute value of the charge and you put that down there as the subscript, and the absolute value of the charge for the sodium then becomes the subscript for the selenium. Now, because it's a +1, we don't need to write a 1 here like that. By convention, we always assume that it's a 1 there, but you can see how that works. So let's then take something like, let's see, what would be a good combination? Let's take something like gallium. Gallium, oh, boo. How come I keep forgetting to change the color? Okay, so we're going to take gallium, and gallium is Ga, and it has a 3+. And we want to combine that with sulfide. And sulfide has a 2- charge associated with it. Now, if we just do this from the perspective of this thing again, let's go back to our seesaw and erase these dudes. Okay. And my gallium has a 3+ charge on it. So it means I'm going to have to do, let's change it to red, 3+, right? And then my sulfur, or my sulfide ion, has a -2 charge. Now, it's not as easy, right, as it looked before, because now you need to add some things. Clearly, it would make sense if we added, well, let me just put Cl above this, and Ga over here. Okay. If I added another Cl to this deal, it certainly would allow the negative charges to catch up, but all of a sudden the 2 Cl's together are going to overweight the gallium, right? So that's not going to work. So what if I add another gallium then to the other side and throw in another? Now, of course, we just did the wrong thing again, because now we overbalanced it, and instead of pushing down on the right side, we're going to be pushing down on the left side over here. That's not a good thing either. Then we go back, and we go ahead and add to our other side a chloride ion over here. Hey, now it works. Woohoo! So now you have a +6 on one side and -6 on the other, and it all balances out. So that means 3 chlorides and 2 galliums. So if we scooch back down here to our gallium sulfide, then we would want to also, if you were to use the crisscross method, I'll just use green arrows here, put a 2 over here, 3 over there. So it becomes Ga2, and then S3. Pretty sweet, huh? So then that's exactly what you saw up here. My 2 GAs, my 2 CLs. The 3 CLs. Sheesh, Chang. Oh, what do I... Jesus. Sorry about that, you guys. I suck. It's sulfur, not chlorine. Jeez. So it's a sulfide ion. Sorry. You can fire me. This is what happens when you have a fake chemistry teacher. They screw up their screencasts like that. Okay. Anyway, now I hope you get it, and you can ignore my silly mistake there. Okay. Let me pause this for a moment. All right. Good pause there. Now, what happens if we decide we're going to start looking at polyatomic ions? This gets a little bit trickier. Remember those polyatomic ions that I just talked about moments ago? Let's take, for example, something like sulfate. And sulfate has a charge of 2- associated with it. And let me scooch this over here. Imagine I want to combine that with magnesium. And magnesium, we know, likes to form a +2 charge. Now, this is going to work out pretty nicely, right? Because we have +2 and -2, so they'll balance out perfectly. And so then all you need to do is write MgSO4, and it's perfectly balanced, and that's magnesium sulfate. it is important that you notice that you name these simply by saying the metal with the polyatomic ions name, so sulfate, magnesium sulfate. All right, so that's easy. But what if we have a combination that doesn't quite match up? Let's say we're going to just put it. We're going to put together a sodium sulfate instead. Okay, so we have sodium, and sodium has a +1 charge, and our sulfate still is going to obviously have a 2- charge. Now we just saw in the previous discussion that you need to do the crisscross method, and that's exactly what you would do. You simply ignore the subscript that's associated with the SO4, right? That's always going to be associated with SO4, so that never changes. And the 1 that you assume here with S, that never changes too. It wouldn't need to in this case either, because you would just simply take 2 sodiums to go with 1 sulfate, right? And there you have it. Sodium sulfate, balanced out. But this can get really tricky if we do it sort of in another way. Let's say instead of taking sulfate, we take one of the things that's a -1 ion charge. So let's go for nitrate. So I take NO3 minus, and I want to combine that with magnesium again. Now it gets a little trickier, right? Looks a little funny, because what are we going to do? Put a 2 next to the 3? No, we can't, because it's not just that I want to have sort of 2 times 3 oxygens, or 6 oxygens. I want to have 2 of these polyatomic ions, the nitrate ions. So in fact, we can make this a little bit easy on ourselves by using parentheses. So we're going to put a parentheses around the NO3, and then have a subscript of 2 outside of those parentheses. Pretty easy, huh? Not so bad. So let's say then we have, let's see, something like ammonium phosphate. Ammonium phosphate. To make ammonium phosphate, you need an ammonium ion. And the polyatomic ion, ammonium, NH4, has a +1 charge. And the polyatomic ion for phosphate, let's see, it's PO4, 3-, right? And if we do the crisscross method here, this gets pretty tricky looking, right? Because now I want to have the absolute value of the 3 is going to go over here. The absolute value of the 1 is going to go over here. Right? You don't have to worry about the 1, but you do have to worry about the 3 piece. So then we have NH4, and then you need to put parentheses around that with a 3 for its subscript, followed by the PO4. Now, it's very important you notice here, I haven't put any charges on this. There's no more charges. Once it combines to make this compound, the charges have balanced. It's a neutral atom, so therefore you don't have any more charges on this thing. So there you have it, ammonium phosphate. Good? All right, so there we have it. That's making ionic compounds where there's actually a transfer of electrons because you're dealing with a cation and an anion. And we've done it now with polyatomic ions, we've done it with monatomic ions, and we've done it with a combination of the two. All right, see you guys on Thursday for our lab. Happy Maya time. Bye.